I'm going to start the recording and talk about news for Units 4 class. This I thought was very cute. So ransomware, once I've been talking to other students about using living on off the land attacks. You know, these days people try to avoid using malware because you will get caught. The endpoint protection will catch you. So what happened is there was a company called Gigabyte. I think they make network interface cards. I'm not quite sure what they make, but they had a driver, and the driver had a vulnerability. And they refused to acknowledge the vulnerability report and just ignored it. So the report went public and released exploit code publicly. So they still refused to patch it. They just deprecated it and put out another driver, but they didn't bother to cancel the certificate on the first one, and neither did VeriSign, which is the certificate authority. So the old driver will still install on Windows machines with a valid certificate. So that's what this ransomware does. It installs that driver, which has a known bug, and then it exploits the driver, and then it can install malicious kernel extensions to take over your machine, which is pretty cute. And this is, you'll always find some door open somewhere. This is like Microsoft's user account control, which was intended to stop privileges from escalating themselves. But in order to avoid irritating users with all kinds of warnings, they took some of the internal Microsoft tools and exempted it from it. So you can just get in by using those tools. And that's the way it always is. Anyway, so these guys hacked Facebook's Twitter account. I saw that yesterday. And then I see they've done a ton of them. And they really seem to be the classic script kiddies. They put up an ad to their web page. If we go to their web page, it's just a sloppy page saying we will find vulnerabilities or something. And they've hacked a ton of people. It's the typical kind of teenage hacker website. It's Our Mind. And ourmind.org, I went and looked at it to see if these guys actually were interesting. And it's just this. It takes a long time to load. And then it's just the kind of stuff you'd see on most script kiddie defacements, hacking requests, assess your corporate network security. All these links do not, in fact, go to Twitter and Facebook or anything. It's all just one thing. This is like Joe Biden's ads that are saying they're just fake web pages. And the Democratic Central Committee from Washington, it's exactly the same. They'll put up this kind of fake crap from like 1991 or even maybe 2001. And whatever you click, it takes you to their services. And here's their service. For $30, they will decide something about your social media accounts. I imagine they're probably just trying compromised passwords from dumps, but who knows? They'll do something for your stuff for $30. If anybody wants to buy this and let me know what they do, that would be interesting. I don't think I'll try it, but anyway, in order to advertise this, they keep hacking people, and so they hacked a lot of people: BuzzFeed, Netflix, Marvel, CNN, WikiLeaks. So you know, and it is absolutely true that all these things are very easy to hack. It's very hard to find all the holes. They hacked Sundar Pichai's, Google's CEO's account. You know, almost everybody's got these online accounts, and they're typically very unsafe. And that's probably a good thing to mention this one. So this was the election result 5 years ago, where this expert checked out this voting thing, and he said it's very dangerous because the website loads third-party JavaScript from unsecure websites, which not just unsecure websites, but websites that use HTTPS, but they use the wrong version of HTTPS. And this is what really caught my attention, because I got the voting app from IO and I scanned it, and it didn't seem vulnerable to me by my standards, which are, it's not the worst app. But if you're going to have a voting app, you're going to be attacked by nation states, people that actually have real resources, real skills, and real money to spend. And so you have to up your threat model. And his point is that these guys could be hacked with the freak attack. And the freak attack is one of a series of attacks caused by the US government because they, in the 90s and the early 2000s, they outlawed exporting strong cryptography to other nations. So they developed export-grade cryptography, which is cryptography that could be put in American products and shipped to nations we don't like, and it was all breakable by the NSA. And of course, 20 years later, it's now breakable by anybody. And there is a ton of legacy websites left over with security from that breakable kind. This is why the crypto community is so dead sending us backdoors and federal legislations on cryptography, because it tends to have these bad side effects. So anyway, and the point is, I don't think this is much of a vulnerability from my point, because you have to use a number field sieve and $100 worth of cloud computing to crack it. It's a 512-byte RSA key, which is the way it was originally designed in the 80s, which was considered unbreakable at that time, and now it is still not trivial to break. I can't assign this to students for homework, but it's possible for an attacker with some skills and some money And this is why I think Matt Blaze and the other election security experts are right. They say nothing on the internet is even remotely secure enough for voting. I would say something that has this flaw is good enough for like banking and social networking and stuff, and that people aren't just going to be sailing into your account like those Armine people. But someone serious that wants to get in will always get in. There's tons of holes. And that's so anyway, I thought that was interesting to compare to these others. So Charming Kitten is, I think, one of the nation state attackers. I think Charming Kitten is Iran. Let's see. Yeah, Iran. They give them these cute names. And unfortunately, Microsoft has recently decided to rename all the APT groups, and they've named them all after metals. So it's vanadium and tellurium. This is a terrible idea because you can't Google for them. You'll find pages about metallurgy. Giving them a normal name is stupid. Microsoft, by the way, is famous for barging into malware analysis and doing stupid things. When they, about 5 years ago, they started getting court orders to take down botnets, and they would take over command and control centers. They would turn out to be ones that had already been taken over by another malware research group in Europe. And, you know, Microsoft just barges in like the 300-pound gorilla and starts doing things sort of like the U.S. does in foreign countries. You'll barge in, kill your leader, say, there, you'll want to be Democrats now. And like, wait, we'll just kill your leader and leave, and you guys will all become just like the U.S., right? And what, you mean that's not what happens? You mean your little warlords just turned into someone 10 times worse than the guy we killed? Well, who could have seen that coming? We thought you just kill the bad guy and walk away like a cowboy movie. So anyway, so these guys are, Charming Kitten is designing malware for Windows, and they're analyzing it here. So here's one that's kind of cute. It messes up your login so that you have to retype the password so you can steal the password. It breaks the password manager that would automatically fill it. So then you have to type it in manually. This is a common trick. I know this is why a lot of people get mad, because smartphones and some web pages disable copy and paste out of some feeling this protects you. And everyone is mad saying, don't do that. That's how password managers work. They paste in the password. Now I can't use my password manager. And that's bad, because people should be using like 25 character passwords that they can't remember or type, controlled by a password manager. And if you make me type it, I'm going to have to turn it into Apple 4 again, you know, some simple thing I can remember. So here's Bitbucket, one of the many online upload sites. And I guess they're using it as a command and control center or something. A lot of people use Google Drive and Amazon machines, Dropbox, and usual stuff. So it's a lot of that stuff out there. Apple about a year ago announced this independent repair program, so other people could fix Apples instead of official Apple certified stuff. Supposedly you could now get official Apple parts, but it turns out to be incredibly abusive and painful, like most dealing with Apple always is, where you have to like make every customer sign a disclaimer saying this is not an official Apple repair shop. They'll probably ruin your device, and you have to buy this expensive stuff. And you know, there's a huge difference between what Apple thinks of as good enough parts and what the average repair person thinks is good enough parts. And you can, of course, get much cheaper stuff, which is good enough, but Apple doesn't like it. And so, you know, it's a tough thing. Apple, this is the thing. Apple, it's also, I can't run Apple in a virtual machine. It's illegal. Apple will punish you if you do. You can't put it on the Hackintosh. You can do it on a hobby level. When you start selling them, Apple will shut you down, because their main profit is selling hardware. The operating system is just a way to get you to buy the hardware. So they very, very much do not want you running Apple OS on other hardware. And they use all kinds of legal restrictions to block that. The biggest mystery in quantum mechanics for more than a century has been the collapse of the wave function. In quantum mechanics, particles are in an uncertain state. You do not say where they are or how fast they're moving. They just have a distribution of probabilities. But when they are observed, they turn out to have only one value. So there is a wave function of probability. And when you observe it, they mysteriously become certain. Uncertain things become certain. This has always been very mind-boggling. And like the Big Bang and other big mysteries in physics, it just sounds like religion. They say, well, when a human looks at it, that's an observation, because humans apparently have some magical spiritual presence which makes them better than like just hitting a rock. That's not a good enough measurement. That rock would remain uncertain. They say, this doesn't really sound like science. This sounds like magic. And Einstein got real upset saying this is bogus. And Bohr liked this interpretation, and it's been that way. That's what I learned in physics. That's what I did. I did quantum mechanics for my PhD thesis, and we didn't question any of this. We used the equations and they work, but fundamentally, they appear to be nonsense. And this guy's finally trying to fix that. They're trying to design an experiment to find out when the uncertain things in quantum mechanics become certain. And his postulate is that they just have a probability of becoming uncertain per second. And if you just leave them alone for a while, they will collapse into a certain state naturally. And it's not that the observer has some magic, cosmic, unphysical power. And that sounds pretty good, and we'll see if he can find ways to prove that. It would close like one of the biggest holes in quantum mechanics. After my warranty ran out, the battery died. Amazon has oh yeah, the iFixit kits are pretty good, but I think they're not officially authorized. So they'll void your warranty in case you care. But yeah, that's good. Anyway, so this is the New South Wales result from 5 years ago talking about the vulnerability. And I talked about that was the freak attack vulnerability, which is pretty good fun. So here's a drive-by attack. Now the drive-by attacks, I remember from the past, are drive-by downloads. And one of the many victims was Safari. Safari was pretty fun about 5 years ago. If you download one file from Safari, it would ask for permission. But if you download more than 10 files all at once, it will just put them on without asking for permission. So that's good, clean fun. You can make a website, and anybody that visits it, a bunch of files go on their machine. And there have been a series of drive-by download vulnerabilities like this. But this one is a layer 2 vulnerability. Their point is people are using these short-range wireless networks for all their home devices. And therefore, if you can get close to the house, you can intercept those signals and mess with them, because all this stuff is typically unencrypted and easy to hack into. So their point is you can get in through smart light bulbs. And of course, people might think smart light bulbs don't matter, but they're an entry point into the network, like the printer. You take that over. It's not that it's of value itself, but now you're in. Now you use that to attack other devices from nearby. And when you're on the same subnet as devices, they typically have no real defenses. They're particularly protected from the internet, but not much from people that are already in the house. So these guys actually made a hacking chain where they take over the light bulb, and then they use the light bulb as the way in and take over everything. So that's the glories of Internet of Things. We'll probably have a lot more of that sort of stuff happening. Anyway, I got, I just mentioned this one. I got another half a minute. F-Secure, Internet Gatekeeper, which I think is software. I'd sort of like to get it. See, this is a heap overflow, just the type we're doing in this class. So it might be fun to actually see how hard this is. They fuzzed the admin panel with Fuzzatron, which I have not used before. Maybe it's worth checking. I haven't found a good fuzzer. And they found a post request with just a bunch of A's in it. And it will overflow on the heap. And then you just take over the machine with a heap overflow. So it's good, clean fun. It's very much like the homework you're going to do in this class. So that might make a good project, and we'll see what you have to do to make it work. Anyway, all right, so let's, there is a hands-on workshop coming on March 15. So I will cancel this class. I haven't put it on the schedule for this class yet. And if you want to come, you can go to that for extra credit. This is basically 123 level stuff, but it seems fine. And Dave Porcello is a fine guy, so he's going to come teach a hands-on workshop. He's got all the details here, so go to that if you like. But I won't have this class that day. I'll be downstairs being the host for this event. So anyway, we are here at 127, and today is the 8th. So we're here. We're going to do format strings. There's no class next week. It's some kind of holiday. Looks like Valentine's Day, but I think it's something else. Anyway, and week after that we'll be here. So then we'll do heap overflows. All right. So let's take a look at format strings, and I've got, as usual, my cloud machine here, and I got my SSH session, and we can play with it here. This is just a standard Drupal machine, Drupal 9 on the cloud, which just like it tells you to use in the project, which is perfectly fine. And let me see if I can find my slides. File open. There we go. All right. So format strings. So we talked about this. The fundamental weakness for everything we do in this class comes from the fact that data is just data, and it could be a program or an image or an address, and the computer doesn't know, and so you trick it into misunderstanding something that was supposed to be a string as executable code or something. So format strings control the output. So since the actual bytes that are stored do not have a type attached to them, which some people have been proposing to add, then you don't know. And so you can take data and you can print it, and then you put this format string in the print statement. So you can print it as a %C and it'll be a character, a %D it'll be a decimal number, %X it'll be a hexadecimal number, and %P it will print as a pointer, which is another kind of hexadecimal number. And you can print the same data in any of those formats. And it's legal to do that. And your computer doesn't know which of them is the right format. So that's pretty bizarre. And so here you see the pointer. And now you can also print with no arguments. and no data. I just print no arguments, %x, 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 and the last one. I don't tell it what to print. And this is what he talked about before looking at assembly language. When you call print and you don't give it any arguments, instead of just stopping with an error message like a sensible language would, C can't do that because it's got amnesia. First, it has find a variable and push it on the stack, find the next variable, push it on the stack, call print. When it calls print, it has forgotten whether it just pushed things on the stack or not. It doesn't keep track of things like that. So it calls print and just assumes that the pushes have happened. And so print then goes on the stack to find what it hopes are variables to print and prints them. And so this will just print stuff, BFFF, BFFF, 400. What is that junk? That's whatever data was on the stack. Randomly, data used for some other purpose. You now have an information disclosure vulnerability. You're seeing stuff that the programmer did not intend for you to see. You're seeing random stuff on the stack. Because of the nature of C, because of its amnesic effect, it never notices that what I'm about to do is stupid in context because it's forgotten the context. So here, the ones we care about most are hex. %x will print it as hexadecimal, and you can put a number in front of it, which just makes it that long and pads it as necessary to make it that long. And we're going to do that because it turns out we have to control how many total bytes have been printed and make it large. So format string vulnerabilities. Now here, you can make a variable only 10 long and put in a thing longer than 10. And any sensible programming language wouldn't, but C will, because when it does the string copy, it has forgotten that the definition was only for 10. The definition for 10 reserves space for 10 and has a pointer pointing to the first byte, but it doesn't store the length anywhere useful. So when string copy goes, it doesn't have anywhere to find out the length and notice that something is wrong, because the design of the language is just kind of sloppy and it doesn't really define strings in a careful way to prevent this, which in retrospect would have been a good idea, but that's not how C works. So you just print this, and like I say, it will just print whatever it finds on the stack, assuming that somebody put variables there, which they didn't. And if you were actually running an interpreted language, even this one statement all by itself is obviously stupid. You have format and no variable, but C does not run command by command. It turns this into several assembly language commands, which then run losing the context. So it would first look on the right to find the variables and push them on the stack, and there aren't any. So then it just runs the print and prints this format statement. It doesn't notice anything is wrong. So that's good, clean fun. So let's play with this one. ED204 is here. And I guess I'll keep these slides here. So if I go here, I just put this stuff here. So here's ED204. And if you look at the code, all right, there's the code. Let me just, there, I'll make this a little bit smaller. It'll probably work. Let's try it again. There we go. So it includes some libraries, in comes main, and it prints, it takes the second argument, which is whatever you put after the name of the program, and it copies it into a buffer, which is only 1,000 big. So this has, by the way, a buffer overflow, but I don't care about that. We're not going to exploit that today. That was last week. Then it just prints it with no format string. And so we can now see what that does. So if I run this, ED204, and I put, whoa, I put nothing there, it tells me you have to have a string. So if I put AA, it prints AA, and that's fine. But if I put in more stuff, if I get up to 1024, it'll run over, but that's not very interesting. What's more interesting is to put in a format string instead of data. If I put %x, now it prints random stuff off the stack. And if I want to make it more readable, I can put like a dot in between. And then the dots will be literal, and the %x, so there I have 4 dot delimited words of data from the stack. And I can have as many as I want, and it discloses information off the stack. And then I could try a different format, which we haven't used before, %n. %n writes to memory. I have no idea why it even exists. It's bloody insane. It takes the data, interprets it as a memory address, and writes to data, to that address. And the thing it writes is the total number of bytes printed so far. So this writes to these locations in memory, just locations that were sitting on the stack. So it wrote to this, which is on the stack, and this, and then it wrote to this, which is in the code segment. It wrote on top of the code, or it tried to, and I think that's why it had a segmentation fault, because by default, you cannot alter the contents of the text section. But anyway, this is madness. So with %n, we can write into RAM. And so %x, we can see what's in RAM. So if we could find some useful address here, we could then write to it and take over the machine. And so the only remaining task to make this useful is to figure out how to control the addresses on the stack and where to write to take over the machine. That's all we're going to do is solve those two little problems. But this is the fundamental issue. We now have the ability to write into RAM. And therefore, it can create a memory corruption. And right now, I got the DOS situation where I crashed the program, and I'm just going to escalate that into a remote control. So this will read 4 words from the stack. This will write 2 words to the stack in those addresses. And so now you might wonder how we're going to control it. And by the way, this affects all the printf family. There are various fprintf, printf, sn printf, sn printf, a whole bunch of C-related print commands. They all have the same flaw, that you can't use them without a format string. And if the user controls the data going in there, they can put in a format string instead of data, and then they can execute these attacks. So by the way, if you want to prevent this stuff, it's actually not much use. It's not a Stack Overflow. Canary values and ASLR and everything will not do anything about it. Non-executable won't do anything about it. That just makes things not executable in the text section or on the stack, but that doesn't really affect me. I'm doing a write directly into memory. Static code analysis tool could do it. You could just audit your source code and say there shouldn't be any print command without a format statement. I don't even know why that's legal. If someone was to ask me, I would just say every print command has to have a format statement. My program in C for a decade. I never made a print statement without a format statement. I didn't even know you could. It never occurred to me to do something like that. Anyway, GCC will warn you, but it won't stop it. So here's your technique. You control a write operation. You just have to find a RAM operation, which will eventually go into the EIP, and then write the bytes to it. Turns out you have to write the bytes one by one. So you byte the 4 bytes to make the 32-bit address. Then you control an address, which will eventually be used by the program. Now you have to put shellcode somewhere, and you'll have to put that address in there. So you do have to find some place to inject shellcode, and you have to have some address you can write to that will eventually end up in the EIP. And those tasks turn out to be pretty easy. So first you have to control a parameter, so we can use this program. And so the thing to do is, if I put AAAA, it prints AAA. Now that data was stored on the stack. It was put on the stack. In order for print to print it, it had to be on the stack of print statement. And it was also on the stack of this ED204 statement. So the A's are in there somewhere, but I don't know where. Well, I can find them, right? Because I have a memory disclosure vulnerability. So I can put %x dot, and I can just put a lot of them there. Somewhere on the stack are those A's. So I just put a bunch of these in, and there they are. That's why I wear this hat. That's what you look for. So I put in the A's, and they're somewhere, and you just find them. And by the way, in real code, sometimes they're like 200 or 300 words down. So you might have to hunt pretty far to find them, but in this simple program, it's just the 4th word. These 3 words are something else. Those 4 words are these A's. So now I've found a word on the stack that I control. So if I want to hit a certain address, all I have to do is put that address here, and then I have to execute a %n command as the 4th command, which will then take this and write there. And now I have controlled the address that I write to. I haven't yet controlled the data that gets written there, but I can now write to a chosen address. So now we can talk, where would you like to write? Well, we talked about this before. There are, in fact, a bunch of places you could write. You could write the return value at the end of any stack frame, if you could find one, but those move around a lot and they're hard to find. The simplest thing is the global offset table. There are other places. There's also a destructors table and your C library hooks. But the simplest thing is the global offset table. That's used to find library functions you're using. So what you do, here's other places you can go. There's a thing called the add exit structure. There's various things that are used at various points in the program, but we're going to do the simplest thing. If you disassemble this with GDB, E204, and then you disassemble main, you'll see all I'm going to do, I'm going to make this a little bigger and quit and disassemble main. All right, all I want to do is look at the functions that are called. So here it calls get PC thunk, which is something about the prologue it always calls. Here it calls printf. Then it calls string copy, printf, put char, and then exit. So the format string vulnerability happens here. I'm going to corrupt memory at that point. Then later on, it's going to call exit. So if I overwrite the pointer to exit, then when it calls this, it will go to the address I fed in. So all I have to do is find out where's the pointer to exit. And that is pretty easy to do with objdump. Objdump minus R, I think, for relocation records. If this doesn't work, I'll look it up. Does it? Yep, R is for relocation records. This gives you the relocation records, which is the address, and so you can find out where exit is, and there's exit, the G library. It's 0804A014. So if I put an address there, a few lines later, the program will jump there. And so now I know where to write. That's my target to write. I just don't know what to put in the target that I'm writing to yet. So that's the program linkage table and the global offset table. Those are two tables that lead to C libraries, and writing to one of them will do it. So I can now make code that will write to it. And think I won't bother doing this one live, but all you do is you feed it in here. I'm going to try putting it in live. So let's put this in GDB, -Q ED204. Okay, so if I run it here, now if I run and I give it AAAA, it will just print AAA. But if I run AAA and now I give it %X, 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 it will run, print, and then it will show me the 4 variables, and the fourth one is the age I put in. So now, if I do this, %N, it will now write to that location, and that will cause a crash, of course, segmentation fault, because 41, 41, 41, 41 is not in one of the memory regions that's allocated for use by this program. So what I have to do is write a little more carefully here. Instead of putting in 4 A's, I need to put in this junk, which is $quote 14 A0 0408. And then this garbage. If I've done this correctly, this will fill it with 0804 A014. And so I can do that. And if I run that, it's going to crash. But notice the extended instruction pointer now contains this strange number 1B. And if I do info registers, you can see I did manage to put that in the EIP. So what happened is I did write to the global offset table, and it called exit, and it jumped to address 1B, and that 1B is what I put in there. And the reason it's a 1B is that's the total number of characters printed, which is 16 plus 12, whatever 1B is, 16 plus 11. So if I were to print something longer, in fact, I should be able to do this. I printed that. If I now put Z over here and go, that's still 1B. I thought it would be something longer, but anyway, I think it's the number of characters printed by the time it hits the %N. And so stuff after that doesn't count. So I'm not quite, I think I might be able to do it. I don't know, let's try this. What if I put something longer here, like 20X? That might do it. Yep, that did it. That meant now I'd printed more characters, so now instead of 1B, it's 27. So that's how you control what it prints there. You just have to make one of these things before it big enough. So now I can write anything I want, but I would need to go up to like 4 billion if I wanted to write all 32 bits here. So what I'm going to do is 1 byte at a time. So the numbers I put in here will just have to be up to 255 or so. That's the game. So now, here's the code to write 1 byte. That's f1.py. Let's get out of here. And cat f1.py. Okay. So this is the address I write to. So the first time I'm going to write to byte 14, the next time to byte 15, byte 16, and byte 17. Each time I write, it's going to write a 32-bit word, but so I'm only going to keep the least significant byte and then move over one and write again and write again and write again. So with 4 write operations, I can write an entire 32-bit word, and I will destroy the next word over as collateral damage, because this one will write 1 byte to some other word, this one will write 2, this one will write 3 bytes. So I'm messing up something else, but I don't care. I'm going to get the data where I want it, and if there's anything important next to it, I'm breaking that and not caring. So that's the game. So this will now do 4 of these operations, XXXN, then %X, %N, %X. This is how it does the 4 write operations, because these things are all sitting on the stack. And so this will find them as they go. So that's the game. And so what you do is you just run this inside the debugger, gdb minus qfs. It's not fs, it's ed 204. Okay. And then I run, let's do, can I do list? I can, that's handy, good. So let's do list 1 to 20. Okay, so here is the format string vulnerability. So I would like to examine memory after that. So I'm going to break at 15. All right, now I'm going to run, and I'm going to start with this one. And then I'm going to info registers. I can only type better. Okay, and ESP is 240 and EBP is there, but it's not doing a buffer overflow, so I don't really care. All I want to do is look at the stack, X20X $ESP. All right, and somewhere on here should be my A's, and there they are right at the start, the 41, 41, 41, 41. All right, so there's the stuff. Now, in this case, what I'd like to do is look at this address, 0804A018, and let me make sure that's right. We were writing, no, it's 14. Okay, this one slide is for an older version. So let's examine that memory. And it is X, 1X, 0X. Okay, X/1X, 0X. Now I put in that address, which is 0804A0, and is it 14? Okay, good. It is 14, good. There we are. So that is what should be there. And this is an address that really points to something that eventually goes to a C library. So now I'm going to run with that other injection string, which I could have stuck in a clipboard, but I forgot to. So we had it back here, and there it is. So I'm going to run dollars quote. Okay, it's 14 A0 0408, and then %X, %N. That should write over it. And now, if I do that examine again, I have overwritten it, and now it's 1B. So that's what's happening. And now if I continue, it's going to try to use that address and crash with 1B in the instruction pointer. So it's working. Now, I just made a program called f1.py, someplace, yeah, f1.py that does it. And so I can run that in the debugger with run $./f1. So let's do that, run $./f1.py. That's what I wanted to do. And now, yes, and now it breaks, and I can examine to see what it did, and that put 37.3f, 47.4f. And that's just the number of bytes printed. So I'm still filling it with a random number I'm not controlling very well. That's what ended up here. So I've now put junk in there, and if I continue, it's going to crash because that's also an invalid number. But now I'd be able to control all 4 bytes. I'm not writing just 1 byte. That's as far as I've gotten here. So now, to put a chosen value in the 4 bytes, I just need to calculate the right values based on these. If I don't, it's 37 and then 3F and 47 and 4F. So I create it here by offsetting them by a certain amount. So if this one here, I think I'll just show it here. This is just the same thing, but now you calculate these values by taking 256 and 256.2 and times 3. You make it much longer so that you can choose a byte, any byte you want. And multiples of 256 are harmless because I'm only keeping the lowest 8 bits. So 256 is equal to 0. Because the right 8 bits are 0 for 256, 512, 1024, and all those. So this is how I'm going to target exactly these values, AA, BB, CC, DD, by calculating these offsets. And so if this works, I'll have the chosen value, AA, BB, CC, DD. So I should be able to just run that one here. Okay, yes. And here's the breakpoint. And when I examine that, now I've got AA, BB, CC, DD. So now that I can do that, I can hit anything I want. So now I need to figure out what address I'd like to put in there. So, all right, now I make an exploit. Now remember, I'm able to put data on the stack. So I'm just going to put exploitable code on the stack. So I'm going to put a NOP sled of 100 bytes and then shellcode of 250 CCs. This is just a dummy exploit. The reason we often do this, we put a NOP sled and then break so we can make sure it's going to work. We hit the NOP sled and it should slide down the sled and hit the break. Then we will know that we were able to find the address and that it's executable there. So this is what I do for starters. This is F3. So let's just run it where we are here. If I run the F3, then it's going to go and hit my breakpoint. And now it's worth looking at the stack. So let's see if this is big enough. Might be X, say 50X, ESP. All right. So here's all my attack. Here's my NOP sled. There's my breaks. So this was the address we're writing to. Here's the other stuff written in the process of creating the write I want. And down here it writes NOP sleds, and then it hits my shellcode. So all I need now is the data I put in here should be the address of this shellcode. So I pick a label here. It looks like FFFFD11C will be here, and that's in the middle of the shellcode, more or less. That's good enough. And that's what I went with. So it was, all right. And by the way, if I continue, I can make sure this works, and it does work. It made it to, it shouldn't have been a seg fault, I think. I thought it should have hit a break. Oh, that's right. This one is not putting that address in yet. This one is still filling the address with junk. So let me run it again to make this clear. If I run this again right here, the only point of this one was to find out where the NOP sled was. This is the same process we've done before. I run to F3, I say yes. Now, if I examine that memory address, it's just full of AA, BB, CC, DD. So this is going to crash. The reason I've done this is I don't know what to put in there. And in order to find out, I have to look on the stack. So when I look on the stack, I now know putting in an address like this is what I want instead of AA, BB, CC, DD. So that I think is F4. And let me just, I think I'll open a second shell so I don't have to keep going in and out of the debugger. Let's see if I've got that one on my machine. Yes. All right. Make it a little smaller. Okay. CD to 127 and then cat F3. Okay, this is the one I just did that puts in AA, BB, CC, DD. And so let's cat F4. Yeah, and this is the same thing, except now it puts in FFFFD1 1C. So this one should actually jump into the shellcode. So that was F4. Okay, so let's run F4. Come on. All right. Come on, stop messing with me. F4 is what I want to run. Okay, this thing is being a little slow and laggy. All right. There, that should work. Okay, so I run it. It prints these things and goes down there. Now, if I look at the address that I've written, it is this, FFFFD11C. And if I look at the stack, D11C is here. So it's in the NOP sled. So now if I continue, it doesn't give me a sig fault, it gives me a break. So it slid down the NOP sled and it hit that CC, which is at FFFFD144, and that's where it crashed. 45 here is the next pointer. So it tried to execute 44, that was a break, and when it stopped, the pointer was pointing here to execute 45. So it did just what it should, slid down the NOP sled and hit the brakes. So now I have verified that I can execute code I injected. Now all I have to do is put in more interesting code. And that is a fairly automatic process. So by the way, the next thing you have to do is get rid of bad characters. And I don't think I'll do this one live, but it's worth seeing here. Oops, get rid of that. Come on, Shift Control P. All right, there it is. So this is something that will write a whole range of stuff. Right at the bottom, you see for I in range of 1, 256, and then it adds these characters. And first I printed all 256 characters, and then you look in GDB and see which one's got there, because the characters will go until it hits one that breaks the string, and then it'll stop. So null bytes will break it. And by experimentation, I found out null bytes 9, 10, 13, and 32 all break it. That is space and tab and a few other obvious characters. All those things break the string, so you have to skip all them. So I need to write shellcode that does something cool, like make a remote shell over the network, and I have to skip all those bad characters. And we know how to do that with Metasploit. So you do it with MSF Venom, and you use the -B command for bad characters. There they are, null, 9, 0A, 0D, 0x20. That's the command that generates shellcode skipping them, which is very nice. And so it makes Python with 590 bytes and so on. So now you just have to inject that code, and that would be my next list here. This was F4. Let's take a look at F5. In fact, I better use less by now. F5.py. Okay, this puts in that address, and yeah, there it is. There's the buffer. Let me make my window a little bigger. Okay, so I have my NOP sled, and then this is the buffer that came from Metasploit, and so now I put the buffer, and I put padding at the end to keep the total length the same, just sort of out of habit, although I don't think that really matters for a format string exploit. And so this will now slide down the same NOP sled and then execute an egg that came from Metasploit. And this is, of course, a simple listener on port 4444, which is the default for Metasploit. So if I run with F5 here and say yes, it hits the breakpoint. And when I continue, it no longer crashes. It executes normally, and it finished the program, executed normally, and forked another process, which is listening. And now if I do sudo ss -pant, and I'll pipe it through more. All right, come on. There's a little bit of lag, which is making me even sloppier than usual. Now I see there's a listening port on 4444. And so anybody that connects to that can take over my machine. I can do it locally, netcat 127.0.0.1, 4444. And oh, I don't have netcat. Okay. Sudo apt install netcat. I think you have to spell it out. Okay, there we go. Glorious netcat. It's what I get for using naked Debian machines. It doesn't have the hacking tools. But all right, now I can do netcat there, and now I'm in. And I just the kind of shell we've seen before. I don't see the prompt, but I can do like ID to see who I am, and ifconfig, whatever I want. So ID shows that I am not root, I am the local user, the user that ran this ED process. But now ED is terminated and this process is still going. By the way, if you're done with this project and you want to get rid of this, you could connect cat in and exit, and that should get rid of it. Let's check that. The other thing you could do is you could kill it. Notice here, you find a PID. You can do kill of that PID. You can always restart your server. There are various ways. Otherwise, it's just going to sit there listening on 4444, offering that to the world. Although, if you've left a cloud firewall in its default configuration, nobody can reach 444444 anyway, which is why it's there. Anyway, so that's the joy of a format string attack. And I got a few cahoots about it. So let me bring up my Firefox, which is the only browser that logs correctly into Kahoot, and I will have to log in because I nuked all my cookies for another class. And then I learned how to use the JavaScript console to kill cookies one by one, so I won't make that mistake anymore. But I did nuke all my cookies before, and so I now have to do this, and this. Now, Berkeley said they can like hear the sound of my typing and learn something about my password. So good luck with that. I don't think it's going to work, but we're going to see now. The Gmail app on my phone confirms whether it's you signing in. And yes, it's me. So now I get in with my glorious two-factor authentication, which has prevented me from being hacked for many years. And now I can try to find the Kahooter. Although anybody hacks me would get extra credit. And I imagine there's ways to, other people got hacked through two-factor. It can be done. If you do it, I'll be happy to give you extra credit. But it's not easy. And I'm not important enough for people to expend the resources so far. So this is 127, chapter 4, I think. Yeah, let's see if it's in my favorites. I might not be organized enough. Apparently I'm not. So we will go here and look for it. All right, chapter 3. It doesn't sort them at all just to irritate you, trying to get you to pay, which I have not done yet. But when they irritate me enough, I probably will pay. Anyway, so I have to hit this button because I nuked all my cookies and I forgot my settings. All right. There we go. And somewhere I can put the answers, like here. All right. But they said at UC Berkeley, it was like about 8 years ago, they said they found they can listen to the typing and they can get some of the entropy out of it. They can tell if you hit the same hand twice or if you switched hands, or if it was the same finger twice. So it gets the entropy from like 7 bits per byte down to like 5 bits per byte. So a brute force attack gets faster, but I don't think that'll be enough information for you to get my password, but give it a shot. All right, I guess that's probably all we're going to get. There aren't that many online. Well, I started with 10. They must have all given up. Anyway, that might have been the last class. Okay, so which one is used when a program exits? The destructors. If you object-oriented programming, like C++, it creates things, and when you're done, it destroys them on the way of shutting down your program. All right. What does %p do? That's a pointer, just another way to write a hexadecimal thing. All right. What defense stops these bugs? Yep, it's a crazy world. Seems like such a simple problem, and yet the defenses don't work. All right. What does %n do? Okay, writes to RAM. I would like to know the thinking of whoever put this in language. That seems like an obviously insanely dangerous thing to put in language. I don't know why. There must have been some good reason for this 30 years ago to put that in C, but it's sure not obvious anymore. C was 79. I guess that's 40 years ago, maybe 50 years ago. Anyway, seems in retrospect like a bad decision. Anyway, what's %d do? That's just a plain hexadecimal number. All right. So R.M. McClory, R. McClory looks like a real name. And O.P. might be initials, but it's not a whole name. My grader might be able to figure it out. Poet, she's actually pretty good at figuring these out. And I have some online people that have actually signed up with names like that. But if you want to give me a better name, you should do it in the next few seconds. So I think I'm going to stop the recording. Okay, good. And then I'll leave the share going.